black hole. So the purpose of this lab was to demonstrate the momentum principle, or Newton's second law, which explains how forces cause the momentum of a system to change over time, and to demonstrate the universal law of gravitation, which describes the attraction between two objects based on their masses and separation distance. So specifically in this lab, we found the mass of a black hole via analysis of a star's orbit, and found the initial velocity necessary for a spaceship to fly from a planet and make it around a black hole and not crash into it, with the initial conditions that the engines fail, so the only forces are gravitational forces of the planet and black hole acting on the spaceship. So here's are the relevant formulas. We used the velocity update and position update from Newton's second law, and then also the rate of change and momentum formulas, and in particular the parallel and perpendicular components of the rate of change and momentum. So in this lab, the forces acting on the star were the gravity of the black hole, whereas the forces acting on the spaceship were both the gravity of the black hole and the gravity of the planet. And since these are non-constant forces, we assumed that the V average equaled the V final for the update formulas. So here we can see the code for the computational model of the initial velocity so if the parallel component of F-net was in the same direction of the motion, that meant that it was speeding up, and the perpendicular component of force just changed the direction of the object. And then we also we have the momentum formula code, and then the parallel and perpendicular components of momentum code as seen. So for the computational model for the black hole's mass, I rearranged the F-net formula to solve for m, which is the mass of the black hole, and got a mass of 1.635 times 10 to the 34 kilograms. And then we also have the F-net and then the parallel and perpendicular components. And then here we can see the computational model and the lines of code for the mass of the black hole. And then to find the initial velocity of the spaceship, we take the mass that we previously calculated for the black hole and put it on this first line of code, which you can see. And then in the scenario, the system was the ship and the surroundings were the planet and the black hole. And then to find F-net, first calculate R, which is just the difference in position of the planet and the ship, and then calculate force. And this line of code combines the step of finding the magnitude of F-net and R hat, and combines it into one step to just find F-net. And repeat this also for the force of the spaceship on the planet. And then to find the total force on the planet, we add the force of the black hole to the force of the planet, or the force of the ship on the planet. And then we also repeated these steps to find force of the black hole on the ship and then the force of the planet on the ship, so we could get the F-net for the ship. And then to find the positions of both, we applied Newton's second law position and velocity update formulas to get those final positions. And then this is those formulas translating into the code. And so this is the computational model. The calculated initial velocity for the spaceship was negative 4.17 times 10 to the 7 for the x component, and then 1.877 times 10 to the 6 for the y component in meters per second. And then the closest distance between the spaceship and the black hole was 1.354 times 10 to the 9 meters. So for the analysis, the difference between the net force and its parallel and perpendicular components to the rate of change in momentum and its parallel and perpendicular components is that the rate of change in momentum can be calculated through observation of the object's position, velocity, and momentum as a function of time, whereas net force requires that we know the mass of the black hole. So they're different in this respect. However, mathematically, when you look at the formulas, they are the same. One potential source of error was that the mass of the black hole is an average of several values, so it may not be totally accurate, but we could increase the accuracy by increasing the number of trials or experiments, which is the number of times passing through the calculation loop. For the what if, in order to enter the orbit but not collide with the black hole, the spaceship would need to have a similar velocity to the planet. However, to not collide with the planet, being in that same orbit, the spaceship would need to have a y component that is slightly larger and an x component that's slightly smaller than those of the planet. So this is an example of an estimate of the necessary initial velocity of the spaceship, taking the velocity of the x and y components of the planet and just scaling the x component down a little bit and scaling the y component up a little bit to give this final velocity. And that's all. Thank you.